Good evening, everyone. Let us continue with our discussion for the eighth lecture. So we shall be today initially be focusing on the design of columns subjected to axial load and uniaxial moment, and thereafter we shall go for the case where there is axial load and biaxial moment. So yeah, so if we see this case, in case of uniaxial load, axial load and uniaxial moment. So in this case, if you see, say for example, if we give a moment which is in the uh, clockwise direction. So in this case, the right hand say edge, okay, the right hand edge will be under compression, right, and the left side basically the extreme edge of the left side, it will be in tension, right? So we have to, our design will be based on this aspect. So this will due to this reason, if we see here, so what happens is, at the outermost edge, because the right side edge is under compression. So in compression, the maximum compressive strain in concrete is 0.0035, right? So this will be in 0.0035 strain, okay, it will have an strain of 0.0035. And uh, we know that up to a distance of three seventh of this one, the in case of beam, we calculated it to be 3 by 7 of neutral axis. In this case, we take the depth, okay, so up till 3 by 7 depth value, the strain will be it will vary, like the 0.002 strain will be at a distance of 3 by 7 depth from the outermost site where compression, the maximum compression occurs. And between the left hand's edge and the strain having point 002 location, the distance will be 4 by 7 d. So yeah, so this is how we have to take into account, we will calculate the various strain as per this definition, and we will understand how this will be used in solving problems. So as you can see here, up to 0.002 the stress will be increasing in a parabolic way, and after that it will become constant, which will have a value of 0.446 fck, which is similar to how we design the sections in case of beams. Okay? So this is the stress diagram, this is the strain diagram, and this is basically referring to the neutral axis distance, and this is the distance of depth. So neutral axis may be outside of the column section, but the 3 by 7 and 4 by 7 value will be inside the depth of the beam. Okay, so how it will be used, we will see in the problems when we solve it later in the coming slides. So yeah, so this is a column the interaction diagram. So this diagram basically helps us to find the p by fck value. Okay, so there are plots, okay, based on different d prime by d values. So d prime is basically the cover, and d is the effective depth. So based on different d prime by d values, there are various column interaction diagrams, which is basically a plot between pu by fck bd and mu by fck bd square. So when we know these two values, we are able to find the p by fck value. So that is basically user. If we know the p by fck and pu by fck bd value, we can find the mu by fck bd square. Or if we know these two values, we can find the pu by fck bd. So like knowing two terms, we can find a third term based on a given d prime by d value. So for this, we basically need the area of steel, grade of steel, and concrete grade. Okay, so this is how it is to be done. So we will understand how it is used. Okay, so let us take this problem. So let us assume that there is a column which is subjected to an axial load of 1200 kilonewton, uniaxial moment of 250 kilonewton meter, and it has an unsupported length of 3200 millimeter, and it is pin connection. So the concrete is of having a grade of M20, and steel is having a grade of Fe415, and there is clear cover of 40 millimeters. So how we will design the sections, okay? So yeah, so as we know, the minimum eccentricity allowed eccentricity value. So if this value, this is calculated by L by 500 plus D by 30. Okay? So if the eccentricity value, which will be found by mu by dividing mu with P, like that is 250 into 10 to the power 6 by 1200 into 10 cube. So if this value comes to be lesser than E minimum value, that means this column is only subjected to axial load. Okay, but if this value is more than this E minimum value, that is allowed value, then that means it is definitely in axial load as well as uniaxial moment. So uniaxial moment component will only be mainly used when the mu by pu value is greater than the E minimum value. Okay, so that is how it is designed. So let us go see how to design this. So initially we will assume a column section 300 by 400 millimeters. Okay, so the E minimum value will be how much? 3200 by 500 plus 400 by 30. So this comes to be 6.4 plus 13.33, and that is 19.73 millimeter. So E minimum value will be 19.73 millimeter, right? So it is basically minimum of 19.73 and 20. So 19.73, as it is less, it will be E minimum. And mu by pu value from the question, mu is 250 and pu is 1200. So it is 250 into 10 to the power 6 by 1200 into 10 cube. So it comes to be 208.33 millimeters. So anyways, it is higher than 20 as well as 19.73 millimeters. So that means it is definitely having the moment component, that uniaxial moment component is there. So we have to take into account that also while designing. So we have to design for moment, right? So if you see here, if we see here, the pu by fck bd value, that will come to be 0.5, and mu by fck bd square value, that will come to be 0.2604, right? So yeah, so we, for like using this, we can find the tensile reinforcement percentage value using the column interaction diagram, which we just discussed, this diagram. So using this two values, we can find this, but which which chart to use, so that will be determined using the d prime by d value. Okay, so these charts are present in the basically SP16. Okay, so we have to refer to that. Okay, so but before that, we have to find the d prime by d value. So d prime is basically the cover. Okay, and d is here the actual depth, right? So yeah, so d prime value is basically the effective cover. So here, as it is uniformly placed, so the d prime value will be same everywhere. So it can vary, like as per SP16, d prime by d values, like the charts are based on d prime by d values ranging at a, at a ranging at a variation of 0.05. So one is at 0.05, one is 0.1, one is 0.15. So it is incremented by 0.05. So 0.1, 0.15, zero point 0.2, like that. So yeah, so let us assume, in this case, let us assume 20 millimeter bar diameter, and d prime value will be therefore this 40, which is the clear cover, okay, plus half of 20, that is 10. So it is 50 millimeter, right? So if we calculate, d prime by d will come to be 50 by 400, which is 0.125. Okay, so if we see the charts in SP16, so like there is no chart for d prime by d value of 0.125. It has to be either 0.05, zero point 0.1, 0.15, zero point 0.2, like that. Okay, so it should be incremented at 0.05 increments, right? So this 1 to 5, we have to take either of zero point 0.1 or 0.15. Okay, now as we know that this, it is related, it is used for calculating the p by fck value, right? So the more the more d prime by d value we take, better will be the percentile reinforcement, okay, reinforcement percent. So ideally we should always take a value which is higher than this value. Okay, so if we are getting 0.125, we could have taken 0.1 or as well as 0.15. Okay, but it is always better to take 0.15 because it will give a higher value of p than the required. So if we give higher value, so definitely it will be a better section, right? So we will use the d prime by d value of 0.15. Okay, so PU by FCK BD value as we calculated is zero point 0.5, MU by FCK BD square value is 0.26, and from SP16 these are the pages for which we can find the column interaction curves based on this d prime by d values. Okay, so as I told you, we got d prime by d value of 0.125, and for d prime by d of 0.1, P by FCK value for the MU by FCK BD square and PU by FCK BD is 0.218, and for the case of d prime by d having a value of 0.15, the P by FCK value is 0.24. Okay, so we will take the higher one, so we will take the d prime by d value of 0.15. So for this case the P by FCK value will be 0.24. Okay, so from this we can find the P value, that is the tensile reinforcement, as FCK value is given to be 20, right? Yeah, so grade of concrete is 20, so P value will come to be 0.24 into 20, which is 4.8 percentage. Okay, so yeah, so the P value is 4.8 percentage, and based on this we can calculate the area of steel reinforcement, which is basically PBD by 100, right? So P is 4.8, B is 300, D is 400, right? And divide by 100 we get it to be 5760 millimeter square. Okay, so for this, okay, so if we take 20 millimeter diameters, okay, so the area of one bar of 20 dia is 314 millimeter square. So the number of bars that will be required is 5760 by 314, that is 18.34. Okay, so to make it uniform, we let us give 20. So if we take 20 numbers 20 of 20 diameter bar, so what will happen is, if we see the there are 10 like 10 20 bars on each side, right? So the distance taken only by the bars will be the length taken, the length of only the bars, okay, it will be how much? 10 times 20, that is 200 okay, and the center to center distance between the end bars is how much? 200 itself. Okay, so that means there will be no clear space. Okay, clear space will be very less, it will be 2.22, so it is almost nothing. Okay, so there will be space constraints. Okay, so therefore it is very important to redesign the longitudinal bars. Okay, so we can use 20 dia bars, either we have to change the section, column section, or if we increase the bar diameter. Okay, so if we increase the increase the bar diameter, so from 20 if we go for 25 okay, so here the area of one bar 125 diameter bar is 491 millimeter square. Okay, and the number of bars therefore which we will require is 5760 divided by 491, right? So that comes to be 11.73, which is equal to 11, right? 12, right? So number of bars required will be 12, and because it is an even number, so we don't have to increase it more. So we can give 6 here, 6 here. Okay, so we can give 12 25 5 bars with 6 in each side. Okay, so in this case if we see, the center to center distance between the n bars will be 195 millimeter, which was same I think in this case also. And sorry, it was different because this is 20, this was 20, so it was 200. Okay, so in this case it is 195 because 25 is there. So the center to center distance between n bars is 195 mm, and if we divide by the number of spacings, which will be 5 because there are 6 bars, so it comes to be 39 right? And the clear space between two bars will come to be 14 so 14 so it is quite good. Okay, 14 there should be at least a distance of 10 okay, so if it is coming to be greater than or equal to 10 so the clear space, so it is a good value. So that means we can give this distribution. Okay, so there will be not there will be no much space constraints in this case. Okay, so we can go for this design. Okay, so now let us see what is the minimum distance between individual bars. Okay, so that again we have to follow some codes. Okay, so if we see here, the assuming nominal maximum size of core core segregate is 20. Like generally we take this value of nominal size of core segregate as 20 millimeter. Okay, so then as per the clause of 26.3.2 page 45 of IS 456, the spacing of bars should be a minimum of the bar diameter of largest bar if unequal, and core segregate plus 5 mm. So bar diameter is 25, and this is in this case it is not unequal, but if we take that also, it will be again 25, and this is 20 plus 5 again 25. That means it should have a minimum distance of 25 mm, right? But here we are only able to give 14 mm, although 14 mm is a good one, but still it is not sufficient as per the IS code. Okay, so that means we have to go for either higher bar diameter or we have to change the section. Okay, so let us change the section for a better alternative. Okay, so let us take the like clear cover is 40 mm only. Okay, so it was yeah, it was given 40 mm only. So yeah, so let us change the section. Let us take it 352 by 450 mm. Okay, initially we took 300 by 400. So yeah, so the PU by FCK BD value in this case will be 0.38, and MU by FCK BD square value in this case is 0.176, which comes out to be 0.18. Okay, and the this one the D value, the D prime value. Okay, so the D prime value is effective cover basically. So this is 40 plus 25 by 2, which is 52.5 mm. So therefore D prime by D value will be 0.116. Okay, and we are taking bar diameter of 25 millimeters only. Okay, so in this case the P by FCK value based on like this also is 0.116, so it is greater than zero point 0.1. So let us take 0.15 only, as I told you why. So using chart 33 page 118 SP16, D prime for D prime by D value of 0.15, the P by FCK value will be 0.135 for this given PU by FCK BD and MU by FCK BD square value, right? So P will come out to be 2.7%, which is the percentage of tensile reinforcement, right? So the area of steel, therefore, it will come to be how much? 4252.5 millimeter square. Okay. So therefore, the number of bars which will be required will be 8.66. Okay, and to make it uniform, we will provide 10. Okay, so we will provide 10 25 mm dia bars. Okay, so that means there will be 5 in this side and 5 in the other side. Okay, and this is having a dimension of 350 by 450 millimeters. So in this case, if we see, the center to center distance between the end bars will come to be 245 millimeter, and the number of gaps will be 4, right? So the center to center spacing will just be 245 by 4, that is 61.25 millimeter, and clear spacing will be 36.25 millimeter. Okay, so in this case 36.25 millimeter will be more than the minimum of all this three, which is minimum of 25 25 and 25, that is 25 only, right? So 36.25 millimeter is greater than 25 millimeter. That means our design is it's safe, and it is as per the codal provision, so it is accepted. Okay, so that means this can be the design. Okay, so that is how we design for the uh, columns having axial load and uniaxial moment. Okay, so now let us go to the second case. Okay, so this means columns subjected to axial load and biaxial moments. So moments are acting in the two directions. Okay, so both in x as well as in y direction. Okay, so let us see how. So yeah, so how to design? So there will, like, for a given PU, MUX, MUY, FY, FCK and clear cover value, we need to choose a suitable section having a dimension of B into D, right? So based on these values, we first choose a suitable section B having a width of B and depth of D, and we have to choose the percentage of steel P. Okay, and based on this we need to compute the P by FCK values. Okay, so here we will be choosing the P value, right? So now for a given P by FCK, D prime by D and Fy value, we find the mu x1 value using the same column interaction curves which we just discussed. And similarly for the given P by FCK and D prime by D and Fy values, we find the mu y1 value. Okay, so that means for a given Pu and P by FCK, D prime by D and Fy value, we find the mu x1 and mu y1 value respectively. Okay, and yeah, so this PUZ value is important to get the alpha n value. So we will see how why it is required. So in biaxial bending case, okay, so axial load with biaxial bending, so we just need to satisfy this, uh, this clause, okay, this equation, that is mux by mux1 whole to the power alpha n plus muy by muy1 whole to the power alpha n is less than equal to 1.0, okay. And this alpha n value directly comes from the puz value, that is the axial load capacity of the column, which is calculated using the equation provided here, that is puz equal to 0.45 fck ac plus 0.75 fy as, okay. And like alpha n is calculated using this ratio pu by puz, where pu is the axial load acting on the column divided by puz, which is the axial load capacity of the column. So puz value is calculated using this equation, which is given in clause 39.6 page 71 456 ISO 2000, okay. And pu is the given value which will be given in the question itself. So if the pu by puz value is less than equal to zero point 0.2, the alpha n value takes a value of 1, and if the pu by puz value is greater than equal to 0 0.8, the alpha n value takes the value of 2, okay. So less than equal to zero point 0.2 it is 1, greater than equal to 0.8 it is 2, okay. And between 0.2 to 0.8 it is increasing linearly, okay. So we need to interpolate and find out, okay. And this is again provided in clause 39.6 page 71 of IS 456 2000, okay. So now let us solve a problem using this design philosophy on how to design uh, and try to design a column subjected to axial moment and axial load and biaxial moment, axial load and biaxial moment, okay. So let us take this problem. So yeah, so let us see this. So there is a rectangular column having a which is subjected to a biaxial bending. So the size of the column is 400 by 500, okay. Concrete is millimeters. Concrete is having a grade of M20. Steel is having a grade of Fe415. The load acting is axial load acting is 1200 kilonewton. The moment bending moment acting at x in the x-axis is 100 kilonewton, and acting in the y-axis is 80 kilonewton, right. So the clear cover is provided is 40 millimeter, okay. And your this one, the steel bar diameter is 25 millimeter diameter, okay. So these are the standard values, and let us give a p tensile reinforcement percentage of 1.6%, okay. So let us see how like will it be able to be a accepted design, okay. So yeah, so let us see. So the effective depth, effective cover, sorry, d prime is 40 plus 25 by 2 is, which comes to be 52.5 millimeter. Percentage of steel provided is 1.6%, right. So the p by fck value is 0.08, okay. So we will use the p by fck and pu by fck bd value to find out the mu from the column interaction curves, where we will get the mu by fck bd square, okay. So let us see how. So yeah, so pu value is 1200 kilonewton as has been given. Pu by fck bd value will be therefore 1200 into 10 cube by 20 into 400 into 500, right. So this comes to be 0.3, and d prime by d value will be 0.105, okay. So in this case, because it is 0.10 almost, so here they have taken zero point 0.1 value, okay. So that is the case, but if it is little more, it is always better to take the higher value because of higher p value, right. So yeah, so here the d prime d value is 0.105, pu by fck bd value is 0.3, so p by fck value is 0.08. So using sp16, okay, so we will get the m by fck bd square value to be 0.12, okay. So based on this, we can calculate the mu x1 value, which comes to be 0.12 into 20 into 400 into 500 square, okay. So that is nothing but 240 kilonewton meter, okay. Similarly, we have to calculate the MUY1 value also. So here also it was here in this case it was d prime by d, here it will be d prime by b, okay, because the axis has changed, right. So here it will be 52.5 by 400, that is 0.13125, and as I told you, we take the higher d prime by d value, that is 0.15, okay. So taking d prime by d value as this 0.15, right. So using sp16 chart 45 page 130, we get the based on pu by fck bd value as zero point 0.3 and pu by fck 0.08, we get mu y1 by fck bd square as 0.11 from this chart. Okay, and from this we can calculate the mu y1 value, which comes to be 176 kilonewton meter. Okay, so now we need to find out the puz value, okay, which using the clause 39.6 page 71 of is 456. So puz equation is 0.45 fck ac plus 0.75 fy asc, right? So the AC value will come to be 400 by 500 minus 400 into 500 minus 1.6 by 100 into 400 into 500, right? So this is reducing the tensile reinforcement area. So it will come to be 1,96,800 millimeter square, okay? And the area of steel will come to be 3,200 millimeter square, okay? So these are the value of AC and AS respectively, okay? So using these values, we can find the PUZ value, which will come to be 2767.2 kilonewton. Okay, and we basically need the PU by PUZ value. So the PU value that will basically come to be 1200 kilonewton. Okay, sorry, that has been given. So PU value has given is 1200 kilonewton, and PUZ value which has come to be 2767.2 kilonewton, right? So therefore the PU by PUZ value will come to be 0.433. Okay, so that is that we get by dividing 1200 with 2767.2. Okay, so therefore the pu by puz value that comes to be 0.433. Okay, so this pu by puz value is 0.433, and as we discussed, if it is less than equal to zero point 0.2 it is 1, and if it is greater than equal to zero point 0.8 it is 2, the value of alpha n, right? But this pu by puz value is between, right, 0.433, so it will be increasing linearly, so we have to interpolate. Okay, so the value of alpha n will therefore be 1 plus 2 minus 1 into 0.433 minus zero point 0.2 divided by 0.8 minus 0.2, that is interpolation. Okay, linear interpolation. So using this we get the alpha n value to be 1.388. Okay, so now these are the values which we have, that is pu value comes to be 1200 kilonewton, mux value comes to be 100 kilonewton meter, muy value comes to be 80 kilonewton meter, mux1 comes to be 240 kilonewton meter, muy1 176, puyz puz 2767.2 kilonewton, alpha n is 1.388, right? So we will find this value. Okay, so this value should be less than 1 if the section is to be safe. Okay, so if you see this, putting the values, we get the mux by mux1 whole to the power alpha n plus muy by muy1 whole to the power alpha n. Okay, so this value comes to be 0.6313. Okay, so this is less than 1, right? So that means that the section which we have designed, like which has been given for column subjected to axial load and biaxial bending, so for that this section is safe. Okay, so that is how we have to design. Okay, so yeah, so that is the case basically, and yeah, so that is how that is what they have tried to this one show here. So basically I think the area that has the area of steel that needs to be given is 3200, right? So yeah, so I think they can, yeah, so you can give this maybe based on this. Okay, so the p value which comes to be yeah, so the p value given was 1.6%, right? So if we give 425 dia bars, okay, so then we will get we can distribute it like this. Okay, so this is how the design can be given. Okay, so yeah, so that is how we will design a column subjected to axial load and biaxial bending. So initially we had studied how to design for axial load and uniaxial bending. Okay, so there we basically tried to find the p by fck value and tried to see whether the clear space between the two diameter, the two consecutive tensile reinforcements are as per the clause. Okay, so minimum the clear space should be higher than the provided, than the formula provided in the clause. Okay, and In the biaxial bending, we basically tried to find out the mu by fck bd square from the in the column interaction chart, and finally tried to prove that mu x by mu x1 the whole to the power alpha n plus mu y by mu y1 whole to the power alpha n value should be less than 1 for the section to be safe. So that is the basic criteria. Okay, now let us go for the design of reinforced concrete slender columns. Okay, so these were all were basically for short columns. Short columns means the slenderness ratio was less than 12, right? That is L by D or L by B, right? So it was less than equal to 12. In case of slender columns or long columns, what is it? It is basically the effective length of the columns by lateral dimension is greater than 12, as just told you, as just discussed now. So the slenderness ratio, that is L by D or L by B, is greater than 12. So that is long column. Okay. So what is the difference basically is that, sorry, so what is the difference basically is that in short column there is generally no deflection E, okay, because it is short. But in case of long column, okay, there will always be some sort of eccentricity, okay, because of the deflected shape, okay. So that's why it is little, its this design is little bit different. So here what we mainly use, what we mainly find out is the beta values, okay. So these beta values are mainly used for finding the effective length, okay. So yeah, so we basically calculate the beta value, that is basically the stiffness ratio, okay. So this beta one is basically, yeah, so for example, if we consider this is a story, okay. So let us consider this is a story, okay. So in this story, this is this is the floor level, this is the roof level, okay, for a particular story, okay. So the beams which are acting in the roof, they are the top beams, and the beams which are acting in the floor, they are the bottom beams, right? So the beta one value is calculated based on this, okay. Sorry. So beta 1 value is basically the Kc plus Kcu divided by Kc plus Kcu plus Kb1 plus Kb2. Okay. So this is basically based on the stiffnesses, we calculate the beta 1. Okay. So that is basically for the top joint. Okay. And for the bottom joint, lower joint, beta 2 value is calculated, which is similar, which is equal to Kc plus Kcl divided by Kc plus Kcl plus Kb 3 plus kb4, okay, that is summation of kbl, okay. So l is signifying lower and t is signifying top. So this is similar, the equation is similar, one is for top joint, one is for bottom joint, okay. So that is how it should be done, okay. So uh, using the beta 1 and beta 2 value, so why it is calculated, as I told you, this is calculated for finding the effective length, okay. So using this chart, okay, this chart is given in figure 26 of IS 456. So this chart is used for finding the effective length value for the given slender column. If the condition is if there is no sway, okay, there is no lateral movement, okay, so then this figure. If there is lateral movement, okay, and if there is sway, then we use this chart, which is figure 27. So without sway, it is figure 26 of IS 456. With sway, it is figure 27 of IS 456. Okay, so here also, based on beta 1 and beta 2 value, we can find out the effective length, okay. So this is the effective length ratio, okay. So the this is such that the design is such that initially we have to determine the beta 1 and beta 2 value. So this is basically we use the substitute frame method. So basically I think you have encountered this method in structural analysis course, okay. So using the substitute frame method, we will basically find the beta 1 and beta 2 value, okay. And for brace frames, the frames which have bracings, okay, so there the beam stiffness, okay, that should be taken as 0.5 times I by L, okay. And for unbraced frames, okay, in this case the beam stiffness should be taken as 1.5 I by L. So if the frames are braced, then the beam stiffness should be 0.5 I by L, and if the frames are unbraced, then the beam stiffness should be taken as 1.5 I by L, okay. So that is how the kb value will vary, okay. So now let us take a problem, okay. So there is a four-storied building, okay. So this is a four-story, okay. So it is having yeah, so four stories. So ground floor, first floor, second floor, third floor, and roof, okay. So there are four stories. The top three stories are 4 meter, and the first story is 4.5 meter. Okay, and the beams. Okay, the beams, so it is a very, it is a uniform. Okay, the bays are uniform. So in the xx direction, so in the xx direction the beams are having a dimension of 250 by 400 millimeter. Okay, and in the yy direction basically the beams are having a dimension of 300 by 500 millimeter. Okay, and the columns are having a dimension of 300 by 300 millimeter. Okay, so how we will design? Okay, how we will proceed? So yeah, so the unsupported length basically as per IS code, it is basically full length minus beam depth. Okay, so the full length in the xx direction, so it is yeah, so in the xx direction basically the full length will be how much? The unsupported length, yeah, the in the sorry in the xx direction the unsupported length basically will be full length minus the depth of the beam, right? So in any story, like for the bottom story it is 4500, that is the full length, minus 400, right? In the xx direction, so it will be 4500 minus 400, that is 4100. Okay, and for the other stories it will be 4000 minus 400, that is 3600. So you can say 3600. Similarly in the yy section, the dimension is 300 by 500, so depth is 500 mm, right? So for the first story it will be 4500 minus 500, which is 4000. So you can see 4000. And for the subsequent higher stories it is 4000 minus 500, which is 3500. So as you can see, higher stories 3500. Okay, so that is how the unsupported length is calculated for the four stories. Okay, now let us see the section properties. Okay, so we have considered this to be a brace frame. Okay, so if we consider the brace frame, what happens is the beam stiffness should be taken as 0.5 I by L, right? So as we just discussed here. So if you see here the column above first story, so they have this one, uh, the columns above first story. So basically there the I value will be same because the dimension is 300 by 300 for every case. So it is 675 into 10 to the power 6, that is BD cube by 12. Okay, and similar is for the first story also, 675 into 10 to the power 6. Okay, millimeter to the power 4. But the actual length will be effective length will be both the actual as well as effective length will be different. The full length will be in the first story it is 4500, and above first story it was 4000, right, millimeters. So if you see here the I by L into 10 cube value for the columns above first story it is 168.75. Okay, and that will be the same stiffness. Okay, and in the first story column it will be how much? 675 into 10 to the power 6 divided by 4500, which is 115 to 10 cube. Okay, and it will also remain the same. In the case of beams basically it will change. Okay, because we have to take zero point 0.5, right? So 222 will become 111 and 521 will become 261. And this is the properties are same because beam in the xx direction it was having a dimension of 250 by 400, right? So the I value would become, the I value would basically become 250 into 400 cube by 12, which is 1333 into 10 to the power 6 millimeter to the power 4. And length is given us, the full length is 6000, that is in both the directions, 6 meter. Okay, and so that is comes to be 222. Okay, the I by L value into 10 cube, and because you have to take half it is 111. Okay, into 10 cube. And in the case of yy, because the dimension is 300 and into 500, so it comes to be 3125 into 10 to the power 6 millimeter to the power 4, the I value. And L is 6000 millimeter because it is having the same length. And I by L value comes to be 521 into 10 cube. Okay, so here also we have to take half beam. Okay, so it comes to be 261 into 10 cube. Okay, so now we have to find the ratio of stiffness. Okay, so both for the xx as well as yy. Okay, so as we calculated, that is important for finding the beta 1 and beta 2 values. Okay, so as we calculate, as we have seen how to calculate. Okay, so the for the roof level, so top there will be only this place, there will be nothing here. So this is 168.75, and that is the new this one, the stiffness at the top. numerator, and at the stiffness of the bottom everything will be added. So 1 is 68.7 5 plus 111 plus 111, that is 0.43. Okay, that is in the xx direction. And in the xy direction, yy direction also similarly, this 111 is 261 here. Yeah, so it is 0.24. Okay, in the third floor case, if you see, there are two. Okay, above that also, below that also, so there will be two times. Okay, unlike the roof level. Okay, so it is 2 into 168.75 by 2 into 168.75 75 plus 111, that is zero point 0.6. And here also similarly it comes to be 0.39. Okay, and similarly if we go for second floor level, we will get, yeah, we will get zero point 0.6, 0.39. First floor level it will be 0.59 and 0.38 for xy direction. And in the ground base floor level, the beta will value will be always 1 because it is ground. Okay, grounded, so it will have like maximum stiffness, so it will 1, it will be maximum value will be 1, right? So yeah, so if considering there is no sway. Okay, so if we consider no sway, so we have to follow the 26 figure. Okay, figure 26. So using figure 26 we will find the effective length value. Okay, so if you see from here, we calculated the beta 1 and beta 2 value for each story. Okay, so for from roof to third story, this is the beta 1 value is zero point 0.3 and beta 2 value is zero point 0.6 in the xx direction. Similarly, from third to second, for the second story, uh, for the third story, this was fourth story. For the third story it is zero point 0.6 and zero point 0.6. For second story it is zero point 0.6 and 0.59. For first story it is 0.59 and 1. Okay, and from figure 26 we find the effective length ratio because we are considering no sway. Okay, so here the ratio will be 0.6875, 0.733, 0.73, 0.85. Okay, by using this we can find the effective length. Okay, so L naught value we know, that is the full length. Okay, so yeah, so sorry, I think that was the unsupported length. Yeah, so L naught value is unsupported length. So yeah, it is unsupported length, so it is basically 3600 at the higher stories. And in the higher story it was 3600, and in the first story it was 4100. Okay, and using this and this we find the effective length, which is 2475 fourth story millimeter, 2639 millimeter for third story, 2628 millimeter for second story, and 3485 millimeter for first story. Okay, so we have to see this the LE by D and LE by B value. Okay, so in this case, so the D is equal to 300 millimeters. Okay, so D's value is 300 millimeters, and this if we see here the 3485, so if we find the slenderness ratio, so ultimately it is coming to be less than 12. So our basically goal is, although we are designing for slender column, our goal is to make the effective length and the slenderness ratio basically come to less than 12. Okay, so by taking the effective length, it is coming to be less than 12. Okay, so that means the design is safe. Okay, so that is the goal basically for going for the slender column. We basically find the effective length such that the slenderness ratio value is less than 12. Okay, so that it is safe. Okay, so yeah, so apart from that, we may consider some additional moments. Okay, so that is as per clause 39.7. Okay, page 71. So additional moments are calculated, can be calculated for both the x as well as for the y direction, right? So in the x direction, the additional moment, which is basically the max value, so that will be pud by 2000 into lex by d whole square. Okay, so p is axial load, d is the dimension, lex is the effective length in respect of the measure axis, and d is the again the depth of the section, right? And similarly may is pub by 2000 into ley by b whole square, where similarly pu is the axial load, b is the width of the section, ley is effective length in respect of the minor axis, and b is the again width of the section, right? So that is this equation can also be used for finding some additional moments. Okay, as per page 71 clause 39.7. Okay, so with this, let us we have come to the end of today's this one, the class notes. So now let us go for the problems. Okay, so let us try to solve a few problems. So yeah, so the first question is, as per IS uh, 456 2000, a column in a frame structure is considered to be as a sway column if its stability index value is a less than 0.04, b greater than 0.04, c less than equal to 0.08, d greater than equal to 0.08, a b c d. So which is the correct value? Okay, so as per IS 456, a column in a frame structure is considered to be a sway column, okay, if its stability index is greater than 0.04. Okay, so that is given in clause annexure E E2. Okay, annexure E clause E2, okay, of IS 456 in page 92. So in order to a column to be a sway column, its stability index value has to be greater than 0.04. Okay, so therefore B is the correct option. Okay, second question, as per IS 456 2000, in a frame structure, if a column is considered to be a brace column, which of the following statements is true? Okay. A. Lateral stability is provided by secondary beam and wall. B. Lateral stability of the structure as whole is provided by beam and column only. C. Lateral stability of the structure as whole is provided by walls or bracing. D. Lateral stability is provided by beam only. So which of them is correct? Okay. So if the column is considered to be a brace column, okay, in a frame structure, so which is correct? Okay, so if you see clause 39.7.1 of IS 456 in the notes section in page 72, so it is written that in case of a brace column, the lateral stability of the structure as whole is provided by the walls and bracing, walls or bracing. Okay, so if you see, only this option is the one which is matching. Okay, so lateral stability of the structure as whole is provided by walls or bracing. Okay, so the C option is the correct option. Okay. Third question, a rectangular column of size 400 millimeter by 500 millimeter is reinforced with 8 number 16 diameters bars. The grade of concrete used is M25 and the grade of steel used is Fe415. The column is subjected to a factored axial force of 1400 kilonewton and biaxial bending. Based on the given data, the PUZ value nearest multiple of 5 according to limit state method in IS 456 2000 is A 2000 kilonewton, B 2735 kilonewton, C 2200 kilonewton, D 2335 kilonewton. Okay, so we need to find the PUZ value. Okay, so that is the axial load carrying capacity of the column. Okay, so what will it be? Okay, so that is provided as per clause 39.6. Okay, so which is PUZ equal to 0.45 FCK AC plus 0.75 FY ASC, and we have also solved it, quite a few problems we have solved in the last class as well. Okay, so you can refer there also. So yeah, so the grade of concrete given is M25, right? The grade of steel basically given is Fe415, right? And yeah, so the area of steel ASC, so it is how much? 16 diameters, that is 8 into pi 8 square, right? Pi d square by 4 or pi r square. So 8 into pi into 8 square, it is 1608.5 millimeter square, and therefore the concrete area will be 400 into 500 minus ASC, right? So it is 400 into 500, right, minus 1608.5, which comes to be 1,98,391.5 millimeter square. So the PUZ value that comes to be 0.45 into 25 into 1,98,391.5 plus 0.75 into 415 into 1608.5 millimeter square divided by 1000, right? So this value comes to be 2732.55. Okay, so this is close to the nearest multiple of this one, 2735. Okay, so therefore the B option is the correct option. Okay, so 2735 kilonewton is the PUZ value, okay, required. Fourth question, a rectangular column of size 400 by 450 millimeter is reinforced with 8 numbers of 16 diameter bars, right? The grade of concrete used is M20 and the grade of steel used is Fe415. The column is subjected to a factored axial force of 1900 kilonewton and biaxial bending. Based on the given data, the alpha n value according to limit state method is IS 456 2000 is 1, 0.55, 0.65 or 2. Okay, so which will be the value of the alpha n value, which can be which has to be which will be correct for this given data. Okay, so here the pu value is given, okay, which is 1900 kilonewton. We need to find the pu's value again. Okay, so here the grade of concrete is M20, grade of steel is Fe415, area of steel is 8 into 16 mm dia, which is 1608.5 mm square, which is similar to the last question only. Area of concrete is 400 by 450, 400 into 450 minus ASC, which is 1,78,000 391.5 millimeter square, right? So the PUZ value as per clause 39.6, it will be 0.45 FCK AC plus 0.75 FY ASC. So putting the values, we get the value to be 2106.17 kilonewton. Okay, so therefore PU by PUZ value comes to be 0.9. Okay, so if you remember, if PU by PUZ value is greater than equal to 0.8, the alpha n value is 2. Okay, so here therefore the alpha n value will be 2. So D is the correct option. Okay, so as you can see, D is the 2 is the correct option. Fifth question, a rectangular column having cross sectional dimension 400 mm by 450 mm is loaded with pu equal to 1200 kilonewton and mux equal to 100 kilonewton meter. For using interaction curve of column, what would be the non-dimensional form of load and moment if the grade of concrete is considered as M20? Okay, so we need to find out the PU by FCK BD and MU by FCK BD square value. Okay, so what it will be? Will it be A 0.333 and 0.062, B 0.456 and 0.082, C 0.225 and 0.032, or D 0.523 and 0.022. Okay, what will be the correct option? So here the PU value is 1200 kilonewton, FCK value is 20, right? And B is 400, D is 450, right? So PU by FCK BD value will be 0.333 and MU value is 100, right? 100 into 10 to the power 6. So MU by FCK BD square will be 0.062. So PU by FCK BD is 0.333 and MU by FCK BD square is 0.062. So A is the correct option. Okay. So as you can see, A 0.333 and 0.062 is the correct option. Sixth question, a square column is subjected to an axial compression and moment about one axis. Uh, the column having gross cross-sectional dimension 450 millimeter by 450 millimeter is reinforced with 6 numbers 16 mm diameter bars divided equally in any two opposite sides parallel to the axis about which a uniaxial moment is acting. If clear cover is 40 millimeter and position of neutral axis is at 500 millimeter away from the highly compressed edge, what would be the maximum strain in the reinforcement located near the highly compressed edge as per the limit state method in IS 456 2000? Will it be 5.953 into 10 to the power minus 3? Will it be 2.943 into 10 to the power minus 3? Will it be 8.435 into 10 to the power minus 3? Or will it be 4.342 into 10 to the power minus 3? Okay. So let us see. So here the width is 450 mm and as well as the depth also 450 mm, and diameter of bar is 16 mm and clear cover given is 40 mm, right? And effective cover D prime is 48 mm. So this is the dimension. Okay, and as we saw in the first slides only, so this is the distribution of the, because considering this as the maximum this one compressive strain occurring, so this will be the distribution of strain, okay, with the distance, with the distance from the most compressive fiber. So the strain will be linear. So yeah, so maximum will be 0.0035 and at a distance of 3 by 7 3 by 7 of 450, it will be 0.002, which we discussed in the initial slides, right? So the neutral axis distance is 500 mm as has been given in the question. So yeah, so we are interested in finding strain at the steel located at D prime distance at the at the reinforcements which are close to the maximum fiber compression fiber, right? This distance, so this place, is at a distance of d prime. So we are interested in finding strain at this steel located at d prime distance from the highly compressed edge of the column section, right? So from the above strain diagram, if we see OAB and OCD, okay, so OA is definitely this distance is 3 by 7 of this one, the D value as we discussed, and this therefore will be XU minus 3 by 7 of D, right? So as you can see here, and similarly OD value, this will be basically XU minus D prime, right? So as you can see here, and AB value will be 0.002, okay, and CD value will be epsilon. So this is what we need to find, okay, epsilon. So from similarity, if you see here, if we say here, so it will be 0.002 by xu minus 3 by 7 into d is epsilon by xu minus d prime. So 0.002 by 500 minus 3 by 7 into 450 is epsilon by 500 minus 48. Okay. So epsilon comes to be 2.943 into 10 to the power minus 3. So therefore the strain at the reinforcement located near the highly compressed edge is how much? 2.943 into 10 to the power minus 3. Okay. So if you see the B option, okay, so B option is the correct option. So as you can see, the B option, which is 2.943 into 10 to the power minus 3, is the correct option. Seventh question. A square column is subjected to an axial compression and moment about one axis. The column having gross cross-sectional dimension 450 mm by 450 mm is reinforced with 6 numbers of 16 mm diameter bars divided equally in any two opposite sides parallel to the axis about which a uniaxial moment is acting. If clear cover is 40 mm and position of neutral axis is at 500 mm away from the highly compressed edge, what would be the maximum strain in the reinforcement located near the least compressed edge as per the limit state method given in IS 456-2000? Will it be A 2.03 into 013 into 10 to the power minus 4? Will it be B, which is 6.381 into 10 to the power minus 4? Will it be C, which is 3.113 into 10 to the power minus 4? And or will it be D, which is 4.312 into 10 to the power minus 4? So which will be the correct option? Okay, which will be the maximum strain in the reinforcement which is near the least compressed edge? So basically it is the opposite question. Okay, so last question we tried to find the strain at this location. Now we have to find the strain at this location. Okay, so the values are almost the same. B is 450, D is 450, phi is 16, CC is 40, D prime is 48, right? And this also we know. Okay, only difference is this: instead of calculating here the strain value, we will calculate the strain value at here. Okay, so if you see here, OAB is also the same. Okay, it is this distance is x, this 3 by 7 into d, so this distance will be xu minus 3 by 7 into d. Okay, and this distance in this case it will be xu minus capital D plus d prime. Okay, so this place is xu minus capital D, and this place is, this location is d prime, so it will be this total distance will be xu minus d plus d prime. Okay, and AB is 0.002 as we saw in the last example only, and we are going to find at EF, which is epsilon. So again, from similarity of triangles, 0.002 by xu minus 3 by 7 into capital D is equal to epsilon by xu minus capital D plus d prime. So solving this, we get epsilon value to be 6.381 into 10 to the power minus 4. Okay, so the maximum strain in the reinforcement located near the least compressed edge is 6.381 into 10 to the power minus 4. Okay, so if you see the B option is the correct option. So as you can see, B 6.381 into 10 to the power minus 4 is the correct option. Eighth question. A square column is subjected to an axial compression and moment about one axis. The column having gross cross-sectional dimension 450 mm by 450 mm is reinforced with 6 numbers of 16 mm diameter bars divided equally in any two opposite sides parallel to the axis about which a uniaxial moment acts. If clear cover is 40 mm and position of neutral axis is at 500 mm away from the highly compressed edge, and the stress at defined strain values in steel is given as 0, 0, 0.00144, 288, 0.00163, 306, 0.00192, 324, 0.00241, 342, 0.00276, 276, 351, 0.00380, 360. Okay, so what would be the maximum magnitude of force that may develop in the reinforcement located near the highly compressed edge according to the limit state method given in IS 456 2000. Okay, so what will be the maximum magnitude of force? Will it be 321.674 kilonewton? Will it be 293.674 kilonewton? Will it be 212.674 kilonewton, or will it be 295.523 kilonewton? Okay, so let us see. So these values provided are mostly the same. So basically what we need to find is maximum magnitude of force, okay, in the reinforcements located near the highly compressed edge. So in this location where we found the strain, okay, so what will be the value of force acting? Okay, so that is the basically the question. Okay, so these values are almost the same. B is 450, D is 450, phi is 16, CC is 40, D prime is 48. Okay, and yeah, so and similarly the strain values are same, okay, and the OA and OD distances are same as we calculated in the question just before the last question. So this also came to be epsilon value came to be 2.943 into 10 to the power minus 3. We also obtained it in the last to last question, right? So the area of reinforcement in near the highly compressed edge, what will it be? So what will it be basically? So there are three number of bars, okay, and one bar is having a diameter of 16, so there is 3 into pi into h square, okay, so that is the total area. So it will be 3 into pi into h square, which is 603.186 millimeter square, okay. And at this strain, what will be the stress? Okay, so for this we will use these values given. So our strain is how much? 0.002943. So 0.002943 is yeah, so it is between this and this, okay. So we have to interpolate, so between 351 and 360 it will be. So based on interpolation the value comes to be 352.584 megapascal or newton per mm square. So the maximum magnitude of force therefore that will develop is this into the area, right? So it is 352 into 584, okay, into 600.186, okay, divided by 1000, okay. So into in order to get into kilonewton, so the value comes to be 212.674 kilonewton, okay? So this value is close to this value is the C option, okay. So therefore the C, that is 212.674 kilonewton is the correct option, okay. So that is the correct option, okay. Ninth question: as shown in the following figure, if a concentrated load P acts at the center of a rectangular column section and moment M x with respect to the y-axis, y-axis, then what would the possible stress blocks be? It is given that positive represents compressive stress and negative represents tensile stress. Okay, so it is very quite easy. So because the moment is acting in a clockwise direction, so in this side it will be under compression, right? And in this side it will be under tension, okay. So this is compression, this compressive stress, and that is designated positive, so this side will be positive. So a out of A and B, one will be correct, okay. And in the second, like in the left hand side, it will be, because this is in compression, this is tension, so this will be under tensile stress, okay. Tensile stress is negative, so this, okay. So yeah, so right hand side is positive and left hand side is negative, so B is the correct option, okay? So as you can see, option B is the correct answer, okay. So B is the correct answer. 10th question: a rectangular column is subjected to a factored axial load of 1200 kilonewton. The column has gross cross sectional dimension of 400 millimeter by 450 millimeter, and effective length about y-axis is equal to 5 meter. The additional moment about y-axis due to slenderness will be equal to how much? A, 375 point, 37.5 kilonewton meter. B, 40.5 kilonewton meter. C, 50.5 kilonewton meter. D, 55.5 kilonewton meter. So what will be the additional moment about y-axis due to the slenderness? Okay. So which of this out will be the additional moment? So as per the clause 39.7.1, page 71, IS 456, which we just discussed. So the at about y-axis, the MUAY value will be PUB by 2000 into LEY by B whole square. Okay. So the PU value is 1200 into 1000. Okay. B value is 400, right? LEY value is how much? 5 meter or 5000, and B is again 400, right? So solving this, we get the value of 37.5 kilonewton meter. So the A option is basically the correct option. Okay, so as you can see, A, 37.5 kilonewton meter is the right option. Okay, so yeah, so with this we come to the end of today's discussion. Okay, so let us again meet next week, and hope you have a good learning in the coming week again. So we will discuss a few problems again next week. So yeah, so with this I would like to end today's session. Goodbye.